In this video we're going to be talking about epoxides, so I would suggest that you read through chapter 14 or the later part of chapter 14 if you're reading Klein to familiarize yourself with what we're going to be working through in this chapter. What we'll do is we'll create an epoxide and then open it in a few different ways to demonstrate the concepts in this later part of the chapter. I've given you a relatively simple alkene and we're going to make an epoxide from this. And one way we can do this is to form a halohydrin and then follow it up with a Williamson ether synthesis. So I'll show you how that works, and we'll start by forming the halohydrin. You should remember that we're going to use Br2 with water. And one thing to keep in mind here is that we form a very special structure when we have the nucleophilic attack by the double pi bond. To illustrate how this works, we're going to have this molecular bromine right here. And since we have the electron density in the pi bond, which would be here, it's going to actually induce a dipole and put a partial positive right here in this bromine and a partial negative here, creating our electrophile right here. So we're going to get this attack right here. At the same time, a lone pair from this bromine is going to come down and fill the hole that's formed here when the pi bond leaves. And of course this bromine is actually going to act as a leaving group. So what happens is we get this intermediate, or this bromium ion. And keep in mind here that I'm not going to draw stereochemistry for the sake of time with this intermediate. But we get this positively charged bromium ion. I'll draw the positive charge here. And then what's going to happen is with halohydrin formation, water is actually going to act as a better nucleophile, and it's going to open up what we might consider a ring complex here, open up the bromium ion. And you should remember that water actually prefers to attack the more substituted position based on the electronic effects, since this positive charge of the bromine eventually, through the transition state, puts a partial positive here, which is more stabilized by the three neighboring carbons. So when it attacks, this bond here will go back on the bromine, and once we've done a proton transfer, that will give us, this molecule right here. So we added the water, and I'm just going to show it as the alcohol after the proton transfer, and then we have this molecule with its enantiomer, because the bromine can be on a wedge and a dash, because that bromium ion can form on either the top or the bottom, if you want to say, of the double bond that we observed here again. And recognize that the carbon that is attached to the OH group isn't going to be a chiral center because we have two methyl groups. So now the question is, how do we go from this halohydrin to an epoxide? I mentioned before that we're going to use a Williamson ether synthesis. So, using what we remember from that, we know we're going to deprotonate the hydrogen off of the alcohol group, and then that's going to do an SN2 attack. In this case, we can just go ahead and use some hydroxide. We'll say that came from sodium hydroxide. That will deprotonate the alcohol, and that will give us this. Let's go ahead and draw it in the same way. And now the Williamson ether synthesis can happen intramolecularly. So what's going to happen is we want to identify the electrophilic position that the alkoxide part's going to attack, and that's actually going to be the carbon that the bromine is attached to. And it'll do an SN2 mechanism from the back, kick off our leaving group, and that will give us an epoxide that looks like this. So we'll have these two methyl groups, this oxygen, the overall general shape of the epoxide, and then we have, let's go ahead and put this on a dash, and we'll have go ahead and draw the hydrogen on the wedge, because that's what we created by the stereochemistry, but we get this epoxide. Now, I will say that the stereochemistry in this example was a little difficult to follow, especially since I drew the bromine on a wedge in an interesting fashion, but don't let that concern you too much. A lot of the other examples are easier to follow. But the main point here is that we can actually create an epoxide from an alkene by doing a halohydrin formation followed by this intramolecular Williamson ether synthesis. Much like on Christmas, but just not as fun, now we're going to open the epoxide. And there are two ways we can do this. We'll start with a pretty intuitive way and just open it with a strong nucleophile. So we should realize that there are two positions in which we can attack to open the epoxide. That would be here and here. So let's say our nucleophile is going to be this sulfur nucleophile. Let me finish the H right there. In these nucleophilic conditions, it's going to work pretty much just by an SN2 process. So we want to compare our two positions in which we can attack. So if we were to try to attack right here, well, that would be a tertiary position and it just wouldn't work too well since we have all that steric hindrance. So that's probably not going to work. Let's say if we were to attack here. Now it's secondary, but it's much more preferred over the tertiary, so that's what we'll go with. So when we have the SN2 attack, we're going to form the bond there that will kick electrons up onto the oxygen, and our product, what we're going to get after this ring opening, is something that looks like this. And since we had an SN2 mechanism, we do get a change in RS configuration at that nucleophilic site. Now, it may not seem like that actually happened since the isopropyl group is still on a wedge and the hydrogen group is still on a dash, but you'll see it more often when we actually draw the epoxide in a general form to look like this, where the ring part is actually coming out towards you, so don't fret. Once we've opened the epoxide, we can actually take care of the negative charge in the oxygen just by adding some water to protonate it, and that would give us, as we would expect, this nice opened epoxide. As an overview, here in nucleophilic conditions, or with a strong nucleophile, the real important thing here was sterics, or how substituted our reactive positions were and how to choose between those. And in this case, we chose the less substituted position. In the next slide, we're going to look how that can be modified based on the conditions in which the reaction happens. We just did an example in which we opened up an epoxide by using a strong nucleophile. And now we're going to do it by catalyzing the reaction using an acid. Before we begin, you should notice that I've modified our starting molecule a little bit. I've added a group here to introduce a chiral center here, and I also have turned the whole molecule around so that the ring, epoxide ring, is facing out towards us. And I've done that so we can view the stereochemistry a little bit easier. Since we're going to open this ring with acid, some simple conditions we can use would just be, well, we'll use this to save time, do acidic conditions, and we'll have some alcohol in here. And you'll see where that comes into play soon. So when we're in acidic conditions, well, we want to ask, how is that going to affect the reaction? We should expect that it should protonate something, and something here that could be important to protonate would be this, the oxygen in the epoxide ring. So if we're in acidic conditions, we would have perhaps a dilute acid, and we'd have our hydronium molecule as the proton vessel, positive charge, and we can have the epoxide abstract a proton. So I'll redraw our molecule down here with our wedges for the epoxide, which is now protonated, gives the oxygen a formal charge. Always keep track of those formal charges. We had the ethyl group, this methyl group right here, the isopropyl group, and the hydrogen atom on the dash. Now let's make some comparisons. How would this introduction of a proton and this addition of a charge affect the reaction with this epoxide? Well, it introduces an electronic character. So if you've read through the chapter 14, if you're using Klein, we can think, okay, let's view it as we're doing the attack. And in this case, our nucleophile is going to be that alcohol we drew earlier. So we have the alcohol, which should attack through its lone pairs, and we know that we have two positions we can attack, here and here. Well, one is secondary, and one is tertiary. From what we viewed before, we should expect that the secondary position would be attacked based on sterics. But by adding the positive charge, we've introduced electronic character. Because imagine this, as you should know as well, as if we were to try to attack here, during the transition state, we're putting a partial positive charge on the carbon, the tertiary carbon, which should be more stable than putting the partial positive on the secondary carbon. So here we have this competition between sterics and electronics. In this case, and it could depend on what book you use, in this case based on Klein, the electronic effects are going to actually win out when you have a tertiary carbon atom. So we will have this attack at this tertiary carbon. So if we draw the result of that, we're going to have the attack, the electrons in that bond between the oxygen and the carbon move up onto the positively charged oxygen. And now that we're going to redraw our molecule, we're going to see something like this. Once it's open, we have the isopropyl group. Now nothing of the configuration that has changed because nothing on this carbon was attacked, the carbonated stream. So now over here, we're going to have that added, what used to be an alcohol, but now it's more of an ether. So as the hydrogen, so it has a positive charge. That's going to be on the dash since it came in from the back, which would put that methyl group on the wedge, a little bit better, and that ethyl group just in the plane of the molecule. And then once again we can get rid of this positive charge over here by with just some water. That'll just do the deprotonation. And thus, since acid is a catalyst, it'll be reformed, and our final product will be something that looks like this. And excuse the bad drawing. So here, electronics actually won out over sterics because the electronic stability based on the tertiary carbon here actually won out over sterics. Or the steric hindrance wasn't enough to overcome that electronic stability that we obtained. As an overview, we know that with nucleophilic conditions, we're really only worried about sterics in terms of choosing which position we're going to attack. And it can get a little confusing when it comes to the acid catalyzed conditions. And a simple way to put it, or to remember it if you're using Klein especially, is that you follow the same patterns using sterics, same thing, unless there's a tertiary carbon. And if there's a tertiary carbon in acidic conditions, then the electronic character brought on by the tertiary carbon in acidic catalyzed conditions is going to win out over anything else. Otherwise, if there's no tertiary carbon in acidic conditions, then you just follow the same thing with sterics.